these prediction intervals will help you to say that something could happen in the future, hopefully the mean, but there can be acceptable deviations from that forecast. So if you get a narrow confidence interval, you could be more confident about your forecast, but if it's too wide, maybe the forecast is not so accurate. But anyway, in practice, we need to use point-based forecast. So we need to specify a specific point. We don't specify a range or an interval. So in this case, will be the mean of this component, because forecast is composed by 5 different values. If you check just the forecast, you will have 5 different values. You will have the forecast by itself, the point-based forecast, and the intervals, the definition of the interval. Okay, we will continue now by creating an auto-ARIMA model. You have already you have that task here, creating an ARIMA model, I think. Creating an ARIMA model. We will create a model, automatic ARIMA model, and we can also check the coefficients. In this case, not regressive 2, but the definition of the model includes the integration factor, in this case 1, so using 1 differential anyway. It's impossible to avoid the differential in this case because we don't have a stationary time series. I've already said that. So what I will do just a different way to create an automatic selection of the ARIMA model using the archaic information criterion or the decay Fourier test, and you will get 2 different values. It will take a while to get this result. Check here, and you get, well, in this case, the same model 210. And for the next one, we apply a test instead of information criteria, we can get a different result. In this case, we obtain a different model. So just be aware that if you use a different test, you can lead into a different definition of the model. Well, I will try to go to this part. I will try to do this task with you. I will try to follow the Bayesian methodology. To do that, I will start splitting the time series into a train and a test set. I have decided to use a test set of 12 or just 1 year. And to do that, I am just using this function. I'm using the length of the dataset. I am subtracting 12 elements. I am saying I will start from the next element, in this case, the following after this one, and I will continue to the length of the exercise. So I will divide into parts, and we can observe that we have this and also this. And if we compare it with the original time series, we can observe that these values are from here to here. No? So yes, is that okay? No, sorry, yeah, it's from here to here. Yeah. So we have the train and the test, but remember we need to transform at least the first one into time series object. So if we plot the data as it, we will see that we have only dots, and this is one indicator that I need to do this part. So I can repeat the same command again, and I will get a proper time series plot. Yeah. Now I will, okay, let's see. It is not necessary. Oh, somebody wrote something and then deleted it. It looks like that. Okay, we'll try to continue. Now we need to check the stationary time series. You have already said that this is not stationary, but I will do it anyway. So remember we had this test. I will use this test, KPSS, and I will check the p-value. As I get this p-value lower than 0.01, I will reject the null hypothesis that this is stationary. So now I can use the Box-Jenkins methodology as they declare how I have to do it. In Box-Jenkins methodology, they say, if it's not stationary, take differences of the data. I will do that. Now I'm using the Box-Jenkins methodology. I'm on the first step. I am creating a different. I am differentiating the time series, and I have this result. Okay, let's see. First differentiation, remove the training element, however, receive that just MA1 by fitting ARIMA with the lower AC, the bottom of this. Can you explain why the ARIMA suggests 210? Okay, let's see. Let's see if I can explain that. It's no question. Let me finish this first. I have already seen that this is stationary. I will just confirm it by using the KPSS. And I should get yes more than that, so I will accept that it's stationary. Now I can continue with the second step. Now I have this. Results, and when I use the Box-Jenkins methodology, they say that I need to focus on this. First, this one. And I have two spikes here. So I will start saying that my ARIMA model will be order 2. Remember that I am using one differentiating, so it will be 1 here. And I will go to this one. You could start with 1, and then you can check this, but I will try to go a bit quicker than that. So remember, these two spikes are here. The explanation. I am not considering this element yet. So this is my first model I will propose now. We'll continue here. We have this ARIMA model, but I need to analyze the residuals anyway. So just getting the model is not relevant at this point. But now I can check the residuals. Now I have a different plot. I don't have more spikes. I have only a negative spike on ACF and PACF. What you I can see in the chat that they say we should fit ARIMA 211. This is a good question. If I see one spike, and if I increase the order by saying, well, but I get an ICF with one spike and I will use it, I could fit the model, I can check the results, and I will get another, I will get the same spike again. So I would recommend you to evaluate this carefully, because if you increase the order of the ARIMA model unnecessarily, you have a risk that you will overfit the model, and this won't be a good model for prediction. Remember that in this case, I am splitting this in train and test. So I'm not using test at this time, but I will now finish with that part, and I will create my predictions. So the most important part now is that I will create predictions for that. I will create a forecast, and I will use the original model I had to create this forecast. And now I will present the forecast of this model I have. Represented like that. But remember, the time series are incomplete, so I'm just predicting the next year. I will use this command. This is not an elegant way to do it, but what I'm trying to do here is just to complete the time series, so you can see a red line on top of the chart. So I'm using these strange labels for X just to complete the 12 points that are missing, just to see how it continues. So you have in blue the prediction, you have in red the time series, and you can see that the prediction interval covers, in this case, the original time series. So it looks like an acceptable forecast, no? Yeah, after seeing that the time series are declining, they are increasing. It's a conservative forecast. Is expected that. But now what I need to do, and I hope I will cover Basili's questions with that. I need to calculate. Sorry about that. I need to calculate the error for each one, and that's something important. I will calculate MAPE and the root of the mean square errors in this case, and I will create a second model. In this case, an auto ARIMA model, but using a different criteria. I have specified in this case by using information criterion, and I will use this now to create a different model. If you want to see what model you get, you will observe that it is a different one. It's also different than the one you have put on the chat, but this is because I'm using a different criterion. And it's expected also that. But if I create all the forecast and also the error metrics for this model, and I will do it very quickly now, you have a different value. I will try to overlap the sequence of the time series over this chart too. And you can see that now we are producing a flat line with also an acceptable confidence interval, but I just want to compare which of the two models are better. And I would like to know your opinion, guys, just to finish before showing the results. Which one performs better? This model, the manual we did with the Box-Jenkins methodology, or this automatic model obtained by using the Bayesian information criterion? Which one will you choose? Let's suppose you are the manager of the organization, and I'm saying we need to create the plan, the forecast plan. And we have this one, the automatic with the flat line, or this one. Christos says manual, yeah. Why manual? Because it has because it's not flat, just because of that. Yes, we can be tempted to choose a model just by checking the chart, but the best way to do it is to check the results. But this is not an easy way. I will compare the manual versus the automatic one, and I can see that the manual gets a slightly better performance for predictions when I'm using the MAPE in this case. But if I check the root of the mean square errors, I get a different result. So I would recommend you to choose to make your decision based on the forecast and also based on the errors. And I will stop here, yeah, just to give you time to continue with this exercise and this discussion. And I'm going back to John. John, if you're there.
Thank you, Carlos. Thank you very much.
Okay.
Okay, thank you.
For the attention of the students. Well, I will stop sharing now.
Okay. All right, well, oh, yes, I think we're back in the room. Okay, well, I hope you found that useful. And I think the questions were interesting because it isn't always clear cut as to whether one method or another will be preferable. And when we move on to prediction, this comparison can be important and worthwhile doing You will sometimes find, by the way, that two models will produce very close results and very close in terms of accuracy as well. So it's not always an absolutely obvious decision. And I know we did discuss this briefly at the drop-in sessions, but please remember that what's being required of you when you're looking at various models is to just work through your logic, work through your rationale, really, I suppose, for what you're doing, and then you should be fine. And a little message from Carlos. So whenever you're looking at prediction, whenever you're looking at whether something is giving a more accurate forecast, then yes, we need to split into the train and test. Yeah. Okay. Okay. Right. In that case, let's move on, and I want to do something a little bit different now on the worksheet. I think it's on page 6. There's an exercise, which is an unusual exercise because most of our exercises are about well, using software and generating results, whereas this is a different sort of exercise, because what this does is it asks you to understand what's going on underneath an equation and how that then relates to testing. So I'll try and explain this. I'm going to first of all try to share my screen. Let me just try to do that. Okay. Carlos, can I just check if the screen is visible, please?
Yes, it's visible. It's okay.
Okay. Okay. So by the way, it's a very short presentation. It's not a full lecture or anything like that. This will be made available on Moodle, and so you will be able to have access to it. So this was the exercise. What it showed you was an ARIMA model, and there it is at the top, 1 minus b, in brackets, 1 minus b to the power 12, in brackets. Both of those are operating on the current observation at time t, which we're denoting by y subscript t. So that's just the variable we're interested in at time t. And it equals c, that's a constant, plus a noise term. So before we get into any detail, when you see an equation like that, you need to think, well, what does that mean? The 1 minus b just means take first differences. That's all it means. Okay, so 1 is the original observation minus b minus that 1 period ago. So that's the first difference. Then we've got 1 minus b to the power 12. So we're assuming monthly data here. And if it's monthly, b to the power 12, that means go back 12 times. So that's the current observation minus the observation 12 months ago. So that's a seasonal difference. So all that really means is, firstly, we take a first difference, then we take a seasonal difference. And when we do that, what we're left with on the right-hand side is a stationary process, because if you look at it, I'll try to explain why this is stationary. C is just a constant, so that must be stationary. That doesn't change at all. Epsilon t, we are assuming here, is a variable, a noise term, with mean 0, constant variance, and no autocorrelation, so there's no pattern in it. And so the c plus epsilon t is stationary. The yt, of course, is not, and it's been made stationary by both first differencing and then seasonal differencing. Now, if we want to try and now express this of the current observation in terms of previous ones, what we can do is we can actually expand those brackets which we've got, the 1 minus b times 1 minus b to the power 12. Although this is an operator, remember, so b is not a variable in the usual sense, b is an operator. byt doesn't mean b multiplied by yt, it means b operated on yt, which takes it from yt to yt minus 1. Despite that, you can actually use algebraic sort of operations, usual algebra, to manipulate this. So that expression 1 minus b times 1 minus b to the power 12, that is actually the same as what we have in the next line. And all that's happened here is the 1 minus b has been multiplied by 1, that gives you 1 minus b. And then the 1 minus b has been multiplied by minus b to the power 12. That gives you minus b to the power 12 plus b to the power 13. Okay, that's all it is. Then we can actually express this using the operator. So 1 operated on yt is yt. b operated on yt is yt minus 1. b to the 12 operated on yt is yt minus 12. And then b13 operated on yt is obviously t minus 13, yt minus 13. Okay, so then it's quite straightforward. All we do is we take the terms on the left-hand side that we don't want and we move them on to the right-hand side, and we get this final result that the current observation is equal to the previous observation plus the observation a whole season ago minus go back one season and go back one period again, plus a constant plus a noise term. So this is why you'll sometimes see spikes when we've got both first differencing, maybe some element of trend, something like that, and seasonal effects as well, that you can sometimes find on these ACFs and PACFs. You'll sometimes see these sort of peaks, not just at the obvious places of 12 periods ago, if it's monthly, but also 13. So you may see that when you look at some of the graphs. Okay, so that was the exercise that was set in the worksheet. What I want to do now is sort of look at it from the opposite perspective, going the other way around, if you like. So if we said, look, that is actually the process. Yt is yt minus 1 plus yt minus 12 minus yt minus 13 plus c plus epsilon t. In mathematics, that's known as a difference equation, because we're expressing something in terms of itself, but some time periods ago. So it's a difference equation. And of course, we can work backwards. So we can say, oh, well, we can express that now using the B operator, the backshift operator, which we do by taking the terms over to the other side and recognizing that yt minus 1 equals byt and so on. And then, because we can use these operators in an algebraic sort of way, we could take that expression, 1 minus b to the 12 plus b to the 13, and we could factorize it. And we're back to where we started at the beginning of the first slide. We're back at 1 minus b, or brackets, multiplied by 1 minus b to the 12, also in brackets. Both of those operating on yt, and equals a constant plus a noise term. Now, you will have seen, if you've looked in any of the help functions in R, that there's quite a bit about unit roots, and this is particularly when there are statistical tests which are being undertaken on time series. And I wanted to explain a little bit about what unit roots are. Now, a difference equation can also be, a difference equation also has associated with it a so-called characteristic equation. Now, I'm not going to get into all the details of this. This is sort of some mathematics which some of you may have covered before, maybe many of you haven't. Don't worry, you don't need to know about this in any depth or detail, but the characteristic equation basically is just taking the function there of the backshift operators and ignoring what's on the right-hand side and what it's operating on. So here's an example for this particular process. That's the characteristic equation. Now we know we've got differencing if the characteristic equation has a unit root, and all a unit root means is that one of the roots of that equation is 1. In fact, there may be more than one root which is 1, as we'll see. And that looks to be the case here, doesn't it? Because if we put z equals 1, the whole thing is going to collapse down to 0. So let me just move on to this point about multiple roots and remind you, I hope remind you, of some algebra. So in linear equations, we know that linear equations just have one root. So if x minus 1 equals 0, obviously the solution is x equals 1. Simple. What about a quadratic equation? So if you think about this one, x squared minus 2x plus 1 is equal to 0. Well, we can factorize that, of course, which is x minus 1 squared equals 0. What you've got to remember now is that quadratics actually have two roots. They don't have one, although in this case it's a repeated root, which sounds a bit strange, but really all it means is you've got x minus 1 times x minus 1 equals 0. So the first root is 1 and the second root is also 1. So it's a repeated root. And that turns out to be relevant, as we'll see. So if I go back to that characteristic equation, there it is. 1 minus z times 1 minus z to the 12 equals 0. By the way, I should just explain why we use the letter z. The only reason we use the letter z is that those roots in general can be complex numbers, as in the second bit, 1 minus z to the 12 equals 0. It's got actually 12 roots. 10 of them are off the real line. But again, if you've not covered too much complex variable theory, don't worry. The point really here is that the first part of that equation, 1 minus z, obviously has a unit root. That indicates first differencing. But the second part of the equation also has a unit root because 1 to the power 12 is just 1. And so 1 is a root of that as well. And that means we've got seasonal differencing. So having that characteristic equation tells us that we've got both first differencing and seasonal differencing that's needed. If I just give a slightly different example at the bottom of the screen, where we have 1 minus z in bracket squared times 1 minus z to the 12 equals 0. In that case, we've still got seasonal differencing, but notice we've got 1 minus z squared. And that means we've got 2 unit roots of z equals 1. And if we have 2 unit roots of z equals 1, that indicates not first differencing that's needed, but second differencing. In other words, you need to difference once, and having done that, you difference it again, and then we should achieve a stationary process, which is what we want, of course, for ARIMA models. Now, okay, so that's a little bit of the theory. What about the unit root tests which are available in R? Well, the first one is NDIFs, and so I've noticed that I've capitalized the N. It shouldn't be capital, it should be just small n there. So NDIFs, that's a unit root test, and it's basically testing the non-seasonal differencing. So these are the sort of effects you get when you get some trend. And we've covered some of this in the lectures, actually. We've already mentioned the KPSS test, and that's used quite a lot. Augmented Dickey-Fuller as an alternative, and R actually has a third alternative as well, called the Phillips-Perron test. So those three are all available within R to test for non-seasonal differences. We can also look at seasonal differencing as well. There's 4 tests available within R. I'm not going to go through the details of all of them. They've all been designed relatively recently, probably in the last 20 to 30 years. And the one which is the default is actually the top one, SEAS, and that's owing its existence to some research work done by Wang, Smith and Heinemann. Again, you don't need to know the details of this. The important point is that both NDIFs and NSDIFs are available there for you to use. And as Carlos was saying earlier, sometimes it's just confirming what you can see anyway in the data, but not always. Sometimes it's less obvious. Sometimes it's not quite so clear whether we need differencing or not. That's as much as I wanted to say about that. Let me come out from that, come back into here. Okay, I've got a question there. So there's a bigger question here about, do complex numbers in general have real life meanings? It turns out actually that they do. They're used quite extensively in fields like electrical engineering. For our purposes, though, when we're looking at differencing, fortunately, we don't have to worry about the complex roots, and you can have complex roots, as I've just pointed out, so that you don't need to worry about those. And for the detection of the differencing, you only need to look at the unit roots. So broadly, can complex numbers or can complex models be interpreted? Yes. The problem, of course, is that interpreting the actual complex number itself is not usually so natural. But in this case, it's actually the real roots that matter. Yeah, so I hope that answers your question, Christos. Okay, let's in that case move on. So Carlos went through the material that overlapped from last week. What we'd like to do now is move on to the seasonal ARIMA part of worksheet 6. And I'm going to do what we've done previously. I'm going to put you in some groups. And what we'd like you to do is share with one another what you've managed to do on the worksheet, but also have a look at the questions that are set there as well, and you can discuss those. And yeah, we've got about 15 minutes for that, so I hope that can be a useful thing for us all to do.